Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be working through the June 2023 Unit 1, Paper 2, and we'll be working through question 3. Now, the first part says Table 3 shows the formulae and oxidation number of the elements of period 3. So here we have our elements, so we're just running across period 3. We have the formula of the oxides that we're going to have to fill in, and we have the oxidation number of the element in period 3 that we're going to have to fill in. Okay? So the question says, complete the following. Write in the formula of the oxides. We're going to exclude the chlorine and the argon. We're not going to write anything for them. And then we're going to write the oxidation number for each of the elements, and we're going to exclude these guys as well. Okay? So here's what we came up with. So for sodium, we have that the oxide is Na2O, magnesium, MgO, aluminum, Al2O3, silicon, it's silicon dioxide, so SiO2. And then for phosphorus, we have P4O10, and then sulfur, we have SO3. Now the oxidation number, when they're in these forms, is +1, +2, +3, +4, +5, +6. So you can see a trend that as you go across the period, the oxidation number is gradually increasing. Now, there are some additional answers that could have worked in this table as well. And so let's just fill those in, just in case, right? You came up with a different answer. For the sodium, let's start with sodium. For sodium, another oxide could have been the Na2O2, and that one is called sodium peroxide, right? So that's a possible answer here as well. It's sodium peroxide, and that one is formed when we have sodium in excess oxygen, okay? So that's when that one would have formed, but it does exist. It is an oxide as well. So sodium in excess oxygen is when we would have gotten this one. And in this one, the oxidation state of sodium is still +1, but the oxygen would have now been -1 in that peroxide compound, okay? So that's a possible answer that could have gone here for the formula of the oxide. Another one is the phosphorus. The phosphorus, we actually have another form of it, which would have been P4O6. And that's when the oxidation state of the phosphorus is now, so in here we're +5, so that's when we are +3, right? And then the sulfur could have also formed a sulfur dioxide. And in that case, the oxidation state of the sulfur is +4, right? So just keep those things in mind. And so this table actually shows the highest oxides of them. So when we're using the highest oxidation number, right? So we use 5 and we got that one. But if we had used the 3, which is a lower oxidation state, we would have gotten the P4O6. And in this case, we use the 6. If we had used +4, which is a lower oxidation state for sulfur, we would have gotten the SO2. Okay, and then we already addressed the peroxide already. But keep that in mind. If you wrote any of these, right, you would have also been correct because the question didn't explicitly say form the oxide from the highest oxidation state, right? So these could have also worked. Okay, and so we're going to move on now to the other part of this question. Right, so the other part says, explain the nature and variation of the oxidation numbers for the elements in the oxides in table 3. Okay, so here's what we would say. The oxidation number of each element in their oxides increases as we go across period 3, and we just kind of touched on that, right? The acidic nature of the oxides is also increasing as we go across period 3. Right, so it actually turns out that these oxides here, so the phosphorus and the sulfur, are very acidic oxides. So keep that in mind. So as we went across the period, we got more acidic in nature, the oxides did. And so these are the more acidic ones there, okay? So let's finish our thought here. In the oxides, we see that the oxidation state of the element is equal to the number of valence electrons on the atom, which is the element's group number, right? So as we go across, we're We're adding 1 to it, and we're changing group as we go across a period. So the oxidation number is the element's group number. And this means that in order to form these stable oxides, all of the valence electrons in the element are used up in bonding, right? Because if that number represents the valence electrons, it means that they're losing all of those to form the oxides, okay? All right, so moving right along, we're now asked to write the equation for the reaction between the oxides of phosphorus and cold water. All right, so I've populated 2 equations here. The first one is for the highest oxide, which was in my table. It was P4O10 solid. If I reacted that with water, I would have gotten phosphoric acid. Okay, phosphoric, there are 4 oxygens there, that's phosphoric acid. And if I had written the lower oxide of the 2, which is P4O6, and reacted that with water, I would have gotten phosphorus acid. Okay? All right, and it turns out that this one is slightly more acidic. The top one is more acidic, so that one would have formed a solution of pH 1. Right, that's an acid. And this would have been a pH 2, the bottom one. Okay, so just keep that in mind. We said that these are acidic oxides, so they're going to form acidic solutions. And just take note of those pHs as well, okay? All right. So this is phosphoric, and this is phosphorus acid. So keep that in mind. Just a difference of 1 oxygens, okay? All right, so let's go along now. All right, so here we are now. So we're gonna study this table of the electrode potential values and then answer some questions, okay? So here's our table. We're just gonna look at the table before we even do anything else. These tables are always written in terms of reduction. So if you notice, they always show the element receiving, right, or accepting electron, gaining electron to go to this form. So this table is written in terms of reduction, right? So whenever you look at the value for anything here, it's telling you how well the thing wants to be reduced, right? If it's more positive, the thing really, right, the compound, the element or the species really wants to be reduced. And so that would make a good oxidizing agent. And so in the table, this is our strongest oxidizing agent, right? That's going to be our strongest oxidizing agent because it wants to be reduced the most based on that value being the most positive in the table. So this is our strongest oxidizing agent among all of them, right? And the lowest value means that it doesn't really want to be reduced. It would rather be oxidized. And so that in the table would have been the strongest reducing agent. Okay? So that's how we kind of dissect these tables whenever we see them, right? The most positive thing is going to be our strongest oxidizing agent, and the most negative thing is going to be our strongest reducing agent. So let me just write what I said beside them. The oxidizing agent wants to be reduced, right? Wants to be reduced. So it's going to oxidize something else to cause that thing to lose its electrons so that it can grab them. It wants to be reduced, and the reducing agent now, it wants to be oxidized. Okay, so just keep that in mind. Okay. And if it wants to be oxidized, guys, what that means is that it wants to lose its electrons. So it's really, really, really wanting to give away those electrons to something else. And so it would reduce something else. It would cause something else to gain those electrons, okay? So the key takeaway, more positive the value is, it's the strongest reducing agent. And the smallest value out of all of them will be the strongest reducing agent that wants to be oxidized. Okay? All right. So in light of that now, here's a question. Which of the following halogens would bring about the maximum change in oxidation number of sulfur? Right? So let's look at all the halogens. We have iodine, we have the bromine, and we have the chlorine. So when we look at their values, right, we're going to see which one is the most positive one, right? So the most positive one turns out to be our chlorine again, right? So that's going to be our strongest oxidizing agent, right? So it's going to bring about right? It's gonna bring about oxidation in the sulfur and change its oxidation number by the most, while it itself will get reduced, okay? So this is our answer here then. That the halogen with the most positive value of standard electrode potential will bring about that change, right? And so that one is chlorine. That halogen is chlorine, okay? All right, so the next part of this question is saying, write one full ionic equation to represent this change. So that maximum change in oxidation number of sulfur. They want a full ionic equation. And if we're going to construct a full ionic equation, we're going to start with our half equations, okay? So what I'm going to do is I'm going to just clear some space here. And what we're going to do is to show the maximum change in the oxidation number of sulfur. I'm going to pick this one, okay? I'm going to pick this reaction here. So let me just box the ones that I'm going to use. I'm going to use this reaction here, which contains sulfur. You could have used the other one too, but let's just use this one for demonstration purposes here. So I'm going to use that for the sulfur. And of course, it's the chlorine that's going to bring about that maximum change out of all the halogens. So this is my other half. So I'm going to write down those two halves now. All right, let's write down those two halves. So the first half, I'm going to put it right here, would have been my 2. So, okay. So because this is the one that wants to be reduced the most, which is our strongest oxidizing agent, then the other half will be the portion that's gonna that will act then as our strong reducing agent. And so we're gonna rewrite it. We're gonna write it in the other direction, right? To show it being a reducing agent, aka being oxidized or losing electrons. So I'm gonna flip this whole thing around, okay? So if I'm gonna rewrite that, I'm gonna write S2O3 2 minus plus 5 moles of H2O. And then I'm showing it losing the electron, so that's why I'm flipping it around. I'm showing it being oxidized because that's what it wants to do. That's what it wants to be. And so I'm writing it like this to show my electrons being over here, meaning that they're lost, okay? My chlorine, that halogen, is a very powerful oxidizing agent. So it wants to be reduced. It wants to be the one gaining electrons. So I write it as it is written here. And then I'm gonna have that being reduced to the chloride ions, right? And so if I want to write a full ionic equation now, I have to make sure that the number of electrons that get lost here are the same that amount that are being gained here. And so to do that, to balance that, I'm gonna have to multiply the bottom equation by 4, okay? And so when I do that, I'm going to end up with this equation being equivalent to 4 Cl2 plus 8 electrons is going to go to 8 chloride ions. Okay? So now what I'm going to do is I can take both of them and then add them together, because if they're going to be reacting and participating in that redox reaction, I'm going to need to add them both together. Okay, so I just draw a line here. I'm adding them. When we add reactions, this is now on my reactant side, right? So I'm going to cancel that with this, because this is on my product side from my first equation, right? So I'm going to cancel that with the 8 because it loses the 8 and this gains the 8. So that cancels out. So then I'm going to write my reactants now. So here's my reactants. I'm going to come up here and write it, right? So here are my reactants from down there. And then the 5 moles of water. And then this guy is going to be a reactant from that half equation. So I'm going to put plus 4 Cl2, right? And then the electrons went away, as I said. So now I put my equilibrium sign. And here are my products from my first half. So I'm going to write them back. 2SO4, 2 minus, plus 10H plus, and then this one, okay, the 8 chloride ions. All right, and so this is my final answer for the full ionic equation. So let me just box that, right? This is my answer. Right? For the full ionic equation. So remember, whenever you're writing an ionic equation, you write your two halves, right? You're gonna write your oxidation half and you're gonna write your reduction half. You make sure that your charges are balanced, right? So your number of electrons that get lost has to be the same that got gained. And then you just add everything together. And so that's what I did. And so we came up with this for our full ionic equation to represent that maximum change of the oxidation number of sulfur. So in fact, the oxidation number of sulfur is being what? It's being changed. That's an oxidation half, so it's actually going to be being increased. And in fact, the oxidation number of the sulfur is increasing from +2 over here when it's in the S2O32 minus, and when it's now in the sulfate ion now, we know that it has an oxidation number of +6. Right? So the chloride, being a very powerful oxidizing agent, was able to oxidize the sulfur from its 2+ state to its +6 state. Okay? All right, so that's all that there is to say about this part of the question. So let's clear this, and we're going to move on to the other part. Okay? So the other part says that now we have NaZ, which is a sodium halide, which gives the following results on testing. So when we bubble chlorine gas into an aqueous solution of NaZ, it gives a brown solution. On addition of starch, a blue-black color forms. All right, so here the wheels should start turning in your head. Okay, what could Z be, right? So then for the second test, they're telling us that we are gonna, when you do the addition of silver nitrate to NaZ in its aqueous form, we're gonna form a yellow precipitate, which is insoluble in aqueous ammonia. So the wheels should really start turning, right? Because we did something like this in question 1, right? And I'll link it here so you can revisit that with the reaction of halide ions, right? These are results that we've seen before in this same paper. So let's go ahead now and see what else is being asked of us here. We're being asked to identify element Z. So right off the bat, guys, my wheels were turning and it told me that Z has to be iodine. Okay? Element Z has to be iodine based on all the things that are being said here. Okay? So let's go ahead and break it down further. We're being asked to explain the reaction taking place in each of the tests above. And we're being asked to include a balance equations in our explanation. So how did we know it was iodine, right? And so we're going to take the first test, for example, right? When we look at the first test, here's what we're doing. We have, I said it was iodine, so I'm going to write the iodine being there, okay? And then just explain the observations in light of that. So say the Z, I said it was iodine, so I put my I there. So I have my NaZ, and we bubble chlorine through that. Right? In the previous question, we said that the chlorine is a very good oxidizing agent. It's excellent at being an oxidizing agent. So what is it going to do? It's going to oxidize the iodide ions, right? The iodide ions are going to go from being I- to I0 in the diatomic iodine. Now, it turns out that this whole thing forms a brown solution, right? And that's what they told us. They told us in the tests that were done up here that a brown solution was formed. And I know that that brown solution is my I2 aqueous. And further, I know that when the I2 reacts with starch, it's going to form a blue-black color, right? And we know that from our redox knowledge that that's how that reaction goes. Whenever we have iodine reacting with starch, we are going to get that blue-black color. Okay, I didn't include that particular one here, that particular reaction here, but we know that from our redox knowledge that that's something that would happen there. Okay? All right. So for the second test, we are adding what is this? Silver nitrate to NaZ, and that's going to give us a yellow precipitate, which is insoluble in aqueous ammonia. So here's the reaction for that one, right? I have silver nitrate in its aqueous form. I'm adding that to my NaI in the aqueous form. What's going to happen is going to be a displacement reaction is going to take place where the Ag will come in and take the place of the sodium. And so I'll end up getting AgI being formed and then NaNO3. It's just a displacement reaction that takes place there. And how do I know it was iodide definitively? Because AgI, that is the yellow precipitate. Again, from question 1, it will be linked here, right? That AgI is a yellow precipitate, which is insoluble in aqueous ammonia. Like no matter how much, even if I have concentrated ammonia and I add it here, it's not going to dissolve. It's an insoluble yellow precipitate. I know that that's silver iodide. And so that's how we can say definitively that the element Z is iodine. That's how we knew for sure. So these are your balanced equations that aid that explanation as to how we got iodine. You could have also written this in just ionic form where you take out your spectator ions. Those would have been acceptable balanced equations as well to include here, right? And so with that, we've come to the end of this question. Definitely give this video a like, subscribe to the channel, and if you look on your left, you will see our next video up, and if you look on the right, you will find our Module 3 playlist where we have tons of more interesting content that will be helpful in getting you prepared for your exam. So thanks for watching, and we'll see you in our next video.